All right, guys. So we're going to start with the first unit, constant motion. I'm just going to start out with the equations real quick, and then I'll actually discuss them more through the notes. But if you are keeping so depending on how you're keeping notes, if if you are obviously doing this at home, the notes are outlined for you. In class, I kind of give you a blank sheet, and you got notes on the left, notes on the right. But we'll discuss variables and units and all that stuff. I just wanted to give you an idea. These are the two equations for this chapter. And again, they're in the note sheet. We will talk about them as we go through these slides. All right, motion. So just to start with, there's ways to represent motion, and one of them is this dot method. It goes back. So today we have motion detectors, and they send out sound waves, echolocation, like bats and dolphins, that kind of thing. Sends out a sound wave, hits the object, bounce back. It knows how long it took to get there. It knows the time, all that stuff. It can calculate the distance, how far away it is. Is it moving? Is it not moving? Uh, and it graphs little dots. So the graph does it today too. Originally, though, it literally dotted ink on paper. There was a carbon disc, a vibrating motor, and the motor vibrated with a certain every single like a repetition. So you knew the time between those dots. You could measure the distance. Um, anyway, that's life before, like I said, there life before motion detectors. But the pictures stayed. So every once in a while, you might come across a picture where it's like these dots, and so I just wanted to give you a heads up where they came from, why we still have them. It's just a representation of the motion, and in this picture, the dots are evenly spaced, and that is where we're starting our studies. Constant motion, accelerated motion. We will talk about, right? The dots would spread out if you started changing speed, that kind of thing. But I'm gonna break it up into smaller chunks for you. The Toy Car Lab. You guys are gonna do something similar, but with the Moving Man simulation. So I'm gonna save that. That's for the lab. Uh, but you'll get that off that relative motion. We'll talk about constant motion. So here we are. So kinematics is just a big word to catch. It's to catch all the motion stuff, right? So instead of having all these types of motions, we just say kinematics, and all it is it's a description. It's a description of the motion without knowing the cause. And even if we know the cause, we're not going to describe it, right? We're just going to talk about the motion. We're describing the motion. And then the comic here. So I wish this sled. The kid says, "I wish this sled had a speedometer so we can know how fast we're going." The tiger says, "I suppose we could measure the hill, time our descent, calculate our rate in feet per minute, and convert that into miles per hour." The kid says, "That sounds like math." Yes, is what the tiger says, and then the kid's like, "Suddenly, I stopped caring." That's where I need you. I need you to I need you to realize we're doing what the tiger's doing. Uh, we're gonna be able to time stuff, measure it, that kind of thing, convert it from time to time. Uh, that is our introduction to physics, or our description of kinematics and motion and that kind of thing. Study of so here the videos. I can't always show you the videos because they're copyrighted on YouTube. So I can show them through YouTube, but I can't link them to here and record them because YouTube's gonna flag me. So I'm gonna describe this one and relate it to something you can relate to. But you're in your car going down the highway. We'll just say 64. Uh, no traffic. No traffic. You're just going at a constant speed. 60. Set it at 60, 70 miles per hour, whatever the speed limit is. And you're just going. Everything's smooth, right? Everything. There's no bumps in the road. Everything's smooth. You're just going along, going along, going along. That's constant motion, right? You don't feel anything. You don't. It's just a nice smooth ride. You don't feel anything. Feels like you're sitting at your desk or just chilling on the couch. Again, nice smooth road. I'm not talking any bumps. That's constant motion. You could close your not while you're driving, but if you were in the passenger, right, you could close your eyes and just forget that you're in a car. Turn up the music so you can't hear the air going by, that kind of thing. That's constant motion. Relative motion is when you're trying to make observations of other cars passing you, right? If you're going 70 and you pass somebody that's going 60, right? It doesn't look like they're going 60 miles an hour. It looks like they're going 10, which is they are going 10. To you, they're going 10. And that's relative motion. We'll talk about that. That's coming. And then acceleration motion, we're going to save for the next unit. But um, that's the second you hit the gas, you hit the brake, you turn left to change lanes, you turn right to change lanes, like that kind of thing. You feel that. That's acceleration. So that's kinematics. in a little nutshell real quick. The ed puzzles. This is up to you. How I do it in class is I would pause myself, and or you can pause me, and I would go to the ed puzzle and watch the scalars and vectors. Entirely up to you. Or you can keep going through this assignment and come back to the ed puzzles and use them as review. So what I do in class is I use the ed puzzle to introduce it, and then I review it. You have the option of letting me introduce it, and then you can go back and do the ed puzzles for the review. Ultimately, it doesn't really matter. I just want to remind you, you do have 2 attempts, so don't rush through it. That first attempt, just take your time, see what happens, and then go through it and see what tripped you up. So here I'm again. Either you watch the ed puzzle, you can pause me, go watch the ed puzzle, come back, or you can, um, or I can introduce it to you, and you can use the ed puzzle as review. So here's where we're at. So scalars. Like it says, number that represents size only, has nothing to do with direction. Someone gives you a scalar number. You have no idea if it's left, right, up, down, northeast, southwest. It's represented by a line segment. Just draw a line. No indication of direction. It's just a line, and then its length, how big it is, indicates. So if it's 1 foot versus 2 foot, you make the 2 foot one bigger. And then just an example here. Could you give scalar directions to a friend to get to your house? No, I can tell you. Like here's uh, right in the center here. I put where I teach. Um, I can tell you I live like 15 miles south of that location. That is, oh, I'm sorry. I can tell you I live 10 to 15 miles away from where I work, but that could be anywhere, right? I can't give the direction. Sorry, my throwing in south, I should not have done. But so I could live anywhere on this circumference, right? That's not helpful. You can't give someone, oh, drive 10 miles, you'll find my house. That doesn't work because you could go which way 10 miles. Uh, so can you give scalar directions? No. Time is a scalar, has nothing to do with direction. Temp temperature's a scalar, has nothing to do with direction. So there are a lot of numbers we use that have nothing to do with directions. We consider those scalars. Uh, Vectors are going to be a little more telling, specifically with the direction. So they're arrows. Think of the V in vector as the arrow. Uh, I got the vector guy from Despicable Me. I just thought it was funny. The first time I saw it, but the 100th time, whatever. The could you so here could you get so sorry, the picture distracted me. Think of V in vector as an arrowhead showing direction. So the direction the arrow points is the direction it's going. In this case it's going to the right or east, or you could say positive, negative, that kind of thing. And again, its length will indicate its size. So if it's 2 feet versus 1 foot, you make it twice as big. Could you give vector directions to a friend to get to your house? Yeah, so if I tell you I live 15 miles south of where I teach, then now, and if I said due south, like you would just go straight down. I know there's not roads that go straight down, but you get the idea. You could find my house. That's vector. Vectors are going to be very specific in giving us the direction with the number. Now, adding vectors real quick. This is sometimes you can do this in your head. Sometimes I suggest just scratching it out on paper. But adding and drawing vectors. So it's called the head to tail method. And when you put them head to tail, you're going to get this a resultant vector that's a combination of the two. And we'll discuss this more in more detail. This is kind of introduction, like I said, introduction to everything. So head to tail. So these first two, I got the white arrow going to the right, I got the yellow arrow going to the left. If I was to add those head to tail, I'd put the tail of the yellow vector on the head of the white vector. The head's the arrow, and then the tail's the backside. But and it will look like that. And then since I started at the start of the white vector. What I call my resultant would be this red vector right here. So if I went 4 to the right and 3 back, right? My resultant would just be that little bit that's 1. That's how we would add vectors, or in this case subtract, but add a negative if you want to do it that way. Trying to and then that's one you can do in your head, sorry. This one I got, let's just say it's 3, 4, 5. I didn't really make it to scale. Let's say, so we'll keep a nice little triangle, right? The white vector is going, let's just say it's 3, and the yellow vector is going up 4. Well, those don't just add or subtract because they're two different directions. So when you have two different directions, you can't just add or subtract them. So we still do the head to tail method. We just move the white vector down here, and then the resultant would be from where you started to where you finished. So it's going to point in the direction from where you started to where you finished. And there's the resultant. So there, and if it was a 3, 4, 5 triangle, I would go 3 to the right, 4 up. So my hypotenuse would be 5 in that case. You could figure out the angle, stuff like that if we needed it. Um, it'll just depend on the time and the question, stuff like that. All right, that's that one. I write out. I mean, I have to write that one out. Some of you guys do that in your head, and you lose me. So here, why do we need vectors? My best example I can give you is just we live in 3 dimensions, right? We can go left, right, up, down, in, out. So we live in 3 dimensions, but we don't talk in 3 dimensions, or even 2 dimensions for that matter. Like this, my example up here. If someone said I live 5 miles at 37 degrees northeast, nobody does that, right? You know what I mean? Go leave the school, go down whatever road 3 miles, and then take a right on blah blah blah, and drive another 2 miles, right? Those are dimensional directions. Same thing if you're walking through a built giant, like you're in a building, and they're like, "Where? How do you get the room?" Whatever. They're gonna say, "Go down this hall, take a left, go to the next whatever." They'll give you some type of frame of reference for direction and some kind of frame of reference for distance. And so we will need to use vectors to sometimes simplify problems down into 1 dimension. And then the comic, I just thought it was funny. Math people might think it's funny. They're all lined up right on the sidewalk, and then here comes this guy cutting across the grass, and then you hear, "Ugh, there goes that Pythagoras guy." And then there's the Pythagorean theorem, right? A squared plus b squared equals c squared. So you might need that for a triangle from time to time. And then here's another instance. So I'm going to talk about distance and displacement in a second. You can pause me and watch the Edpuzzle and then come back to me, or I can introduce it and then you can use the Edpuzzle's review. Entirely up to you. Here's so distance versus displacement real quick. Distance is just total how far you went. And then displacement is specific to how far you went from straight, so how far you went in a straight line from where you started. Um, Again, this is all formal definitions are all written out in the notes. So my little version of it is still it's the definition, but if you want the formal like how it is out of a book, that's the note sheet. All right, so um, if you're walking, so here's my little stick guy. We're in that little A corner. I'm going to go from A to B, right? How far did I go? Well, how far could have two answers now. It could have how far total did I go, distance, or how far am I displaced? So we need to be a little more specific sometimes. And then I'll tell you when the difference is or how you can tell the difference. Actually, I'm going to tell you right now. If I go A to B, we all agree that's 3 meters. My displacement is also 3 meters. In this instance, they are the same. Now, why are they the same? Because I didn't change direction. I just went in a straight line. If you're always going in a straight line, never change direction, then distance and displacement don't change. They're the exact same thing. They're always going to line up. Now, A to C, right? You went 3 up and 5 over. That's a change in direction. So your distance is 8, 3 plus 5, but your displacement is the hypotenuse of this of the triangle you just made. If you could go from A to C, that would be your displacement. Or even if you couldn't go A to C, you're still from where your position, you displaced yourself. 3 squared plus 5 squared equals the hypotenuse squared, and we would take the square root to get that answer, whatever that is. That's A to C. So in that case, they're different because you change direction. Same thing's going to happen A to D. Now you're going to go 3 plus 5 is 8 plus 3. Now we went 11 meters. But what's our displacement? It's 5 meters. And then I've been leaving this off. When you give displacement, you should also give direction. So from A to C, we should have given some angle. From A to D, I would just say to the right or east. Usually we'll say the compass directions, northeast, southwest. So I went 5 meters east. And when we'll use positive negatives too when we start doing it more. But right, I'm displaced 5 meters to the right of where I started. That is A to D. Now A to A. So now I'm going right I'm going all the way completely around the circle. 3 meters plus 5 meters is 8, plus 3 is 11, plus another 5 is 16. So total distance I walked around the perimeter of that rectangle was 16 meters. What's my displacement though? Just 0. Yeah, I didn't go anywhere. I didn't displace myself based on where I started, right? I ended up back where I started. So again, anytime you change direction, they are different, and then you got to stop for a second and make sure you're taking that into account, right? If you change direction, you got to make sure the question, what is the question asking for? Is it asking about distance? Then I just add them all up like normal. If it's asking for displacement, then I got to do straight line from where I started to where I finished. All right, and now, so again, another Edpuzzle. Sorry, they're short. On here, I say 10 minutes. They're probably like 6, 7 minutes. I'm just estimating that you might need 10 minutes to do it with the questions, but they're not meant to take up much of your time. Just a quick little intro to it, or keep going with me. The Edpuzzle will be your review. So again, you can pause, go watch the Edpuzzle, and then come back for me for a review, or I'll introduce it and the Edpuzzle can review it. Oh, yeah. So here we go. All right. So what is average? Now, there's the equation down. Well, let's talk about the equation, and then we'll go back to the questions. Anytime you see a variable with just a bar over it, they're telling you that that's average speed. It's not initial or final. If you see a variable like this v here with an I, um, that's initial. I is initial. If you see a variable with an f, that's final. So this v does not have either. It has a bar. It's telling you that it's average. So anytime you don't see a little subscript I, f, or anything for that matter, it's an average. Uh, and then you get an average like any average you would do, right? You add them together, divide by 2. If there were 3 of them, you'd divide by 3. You'd add them up, divide by 3. Um, so we're usually dealing with initial and final, and so we just have 2 typically. What is your average speed? So this question back here. What is your average speed if you travel 60 miles per hour for 1 hour and 70 miles per hour for 1 hour? 1 hour? Does the time and distance matter? It turns out they don't, right? Because you did the same. You did 60 miles per an hour and 70 miles per an hour. So proportionally, those are the same. So I can just do 60 plus 70 divided by 2, and I get 65. So on average, for that 2 hour trip, I was going 65. Wasn't going 60 the whole time, wasn't going 70 the whole time. On average, I was going 65. What is your average speed? Now, the second question, what is your average speed if you travel 60 miles per hour for 1 hour and then you do 70 miles per hour for 2 hours? Then you got to modify this equation a little bit. Now, I made the numbers easy so you could do some proportion thing. Does time and distance matter in this one? Yes. And then that's when we go into, we can be more specific about how fast we're going. Now we got to look into how far we went, how long it took, and there's 2 ways to do that. There's 2 ways to get how fast. How fast is just how far over how long. Uh, we can do it the speed way, which is just total distance. You just take the total distance and divide by the time. Delta means change. So change in time. So it'd be final time minus initial time. So if you started at 0 and you drove for an hour, then your delta t would be 1 hour. If you started 30 minutes into the trip, 30, and then went to an hour, like then it would only be 30 minutes. So the problem will be clear on what delta is, but typically we start at 0. Same thing with delta d over here. I'll talk about velocity in a second, but again, it's niche. It's always delta always means change, and it's always final minus initial. Um, so so back to the difference in the equations. Speed is based on distance. Velocity is based on displacement. So those are 2 ways to get how far. So because there are 2 ways to get how far, there are 2 ways to give how fast, the speed or the velocity. We are accustomed to giving speed. Velocity is just going to throw in a direction. And then the vector notation, the V I have off to the side in the box there with the arrow over it. When you see vectors with arrowheads over it, so when you see variables with an arrow above it, it's representing a vector. So velocity is a vector. So this v you could actually, if you wanted to be more clear, to separate this v from this v, I probably should put a little arrowhead. I'm not going to be that picky about it. Just so you know, it's average and it's a vector. We're good. Discuss units. The units will always the units are always going to be base metric. So what do we measure distance and displacement in? Meters. Could be feet, could be miles, but for the base metric, it's meters. What do we measure time in? Again, could be seconds, hours, minutes, days, years, like anytime. We're going to use base metric, which is seconds. So you get meters divided by seconds, or meters per second, and that's a speed or a velocity. It's just like our miles per hour, right? It's a distance over a time. But you can always get those units from how the equation works out. And then where have we seen this? You have not seen this yet. You are about to do, when you do the lab, an equation similar to this one, you will get from the lab. It won't be formatted like this, so don't just say v equals d over t. That won't work. But it'll have you'll see it when you get there. All right. Problem. So we're uh, this is in class. We would jump to problems. You guys are going to get it in a little bit, a few more days here, depending on how you're working through the schedule. But so we'll come back to that. Frame of reference, real quick. All right, guys. Here, few more slides here. All right. So we need a way to define where we are and where we're going. So we use a frame of reference. You can think of it as a point of view. It's your XY axes, and when you are the center point is your origin, is your start point, your 0, 0. Now we do live in a three-dimensional. We can go left, right, X, Y, Z. We can go left, right, up, down, in, out. We can always take our left, right, and then turn it so it's in and out, right? So we can simplify everything down pretty much to an XY axis. And then so 0, 0. So is it, and then my question here is, sorry, and then I think I said this. We need to determine our position. So we need a starting point. And then that's our frame of reference. Our 0, 0 point. Used is a negative number. Yeah, is a negative number smaller than 0? It's a yes and a no. We need to be cautious. What are we talking about? If it's just -2 and 2, then yeah, -2 is smaller than 2. I have 2 less than 0. That's a math, right? That's common in math. Physics, we're going to be measuring physical things. So, like, can you measure something smaller than 0? No, it doesn't exist. Can you go slower than 0? No. So what happens to us is negative is going to be a direction. So negative for us is left or down, and then positive for us is right or up. And then we'll talk more about that as we're going through stuff. So motion and frame of reference. So you can see different. Well, here, let me give you my example here. So let's say hypothetically you wake up on a plane and look out the window. So you got on a plane, for whatever reason you fell right asleep, and then you're just looking out the window. So here's your picture, right here in front of you. Here's the question: are you moving, or is the plane still sitting on the runway? Right? Like if when the plane reaches cruising speed, it's pretty smooth. Like they'll turn on the light, like hey, you can get up and walk around, go to the bathroom, whatever. Um, it's pretty smooth. And then maybe that blurry background is clouds, but then maybe it's fog and you're still sitting on the runway waiting to take off when the fog clears. So how do you prove if you're moving? Is there an experiment that can be done at rest that changes while moving at a constant speed? Like, I'm gonna give you the answer, but like, is there anything that you could do experimentally that could prove that you're actually moving? Now, you could look out the window and there's going to be context clues, right? You might see something in the background moving by, but in this situation, if it's like foggy and the engine's on, right? They're warming up the plane. You don't know. Uh, and so and then what is the difference between constant speed and changing speed? The second you change speeds, you can feel that. So if there's a little turbulence, like a little air hits the plane, then you know you were moving. The pilots hit the gas and start taking down the runway, you feel that, right? You feel that acceleration. That's a change in speed. What we're talking about right now, though, is constant speed when you cannot tell the difference. So it's nice, smooth, no bumps. Again, your visual clues are like not there. So it's not a limitation of your brain. It's not a limitation of technology. It's just physics says there is no difference between being at rest and moving with a constant speed. And then my parking lot story, I feel like we've all experienced this. You're sitting in the car beside you, like in a parking lot, or at a light, and the car beside you either backs up, pulls forward. You think your car is moving. You think they're at rest and you're moving. Again, not a limitation of our brain. It's just how physics works. My story, real quick. I pulled into the space and hit the brake, and at the exact same time, the guy beside me is backing out. So this all happened so quickly that my because my foot's already on the brake, and I'm like, I'm hitting the brake. Why aren't I stopping? And then ahead of me is a little wall, like a building. And so now at this point, I'm standing on the brake, like trying to stop the car. And then I just bust out loud. My kid's in the back, like, what is wrong with you? Um, Once I realized that the guy beside me pulled out. But that's again not a limitation of us. It's just it's physics, and this is what we call relative motion. is the law of physics. All motion is relative to someone else, right? Their frame of reference. How you see something is dependent on you, on where you are. So tennis ball, if you this one's tricky. I, demos are tricky to do on camera. I'm going to try to do some for you, but this one we'll just walk through. If so, if I was just sitting here, we don't have, I don't know if you can see this, and I just it's not really exciting. I just toss this thing straight up and down. Right, you're at rest, I'm at rest. This thing goes up, comes down. We'd all agree that we saw picture B. We saw the exact same thing. I'm at rest, you're at rest. We're all considered to be in the same frame of reference. If I were to walk across the room, right, and record this, right, you would see it go up here. And as I'm walking across the room, right, if I was walking while throwing it, it would also move forward and I would catch it over here. From your frame of reference, you were at rest and I was moving. You saw picture A. From my frame of reference, since here's me. I threw this up and I'm just walking, I catch it. Right? The whole time that thing's above me. So I see picture B. So we see two different things because we were in two different frames of reference. Whose frame of reference is right, A or B? You can't ask that. Well, you can ask that, but we're both right. There's no right or wrong. You can't say I'm right and you're wrong, and I can't say you're wrong, I'm right. We saw what we saw because the laws of physics work everywhere. If we start saying that you were right and I was wrong, then you're telling me my laws of physics changed just because I walked across the room. And I think all of us know that that's not true, right? You get in a car, life doesn't all physics, the laws around you don't suddenly change. You know, nothing weird happens. Um, so must the laws of physics work everywhere? Our assumption is yes, that it doesn't make sense that there'd be some invisible line where you enter this new frame of reference and then all of a sudden the laws of physics break down. Now, are there extremes? Are there black holes? Yes. Do weird things happen around black holes? Yes. It's still not breaking the laws of physics. It's just inside the black hole, we don't know all the physics. Um, uh, what else do I got for you? And then there's some weird stuff that happens when you go really fast. But again, not breaking the laws of physics. It's just taking the laws we know of and expanding them. But Edpuzzle, relative velocity. So relative motion. So here's that was a little introduction to relative motion. The Edpuzzle kind of goes through and gives you more details. You can use that as you can pause me and go use that as the introduction, or you can stay with me. I'll introduce it, and then you can go do the Edpuzzle later for review. But all motion is relative. This, unfortunately, is another video that I cannot show you, but it's a Mythbuster video. And if you type this in, truck being driven at the same speed that the soccer ball is shot, but traveling in opposite directions, probably have to add Mythbusters. It's worthwhile looking up. But again, it'll tag me for copyright stuff if I post it. If I post a copyrighted video. So I'm going to explain it, but they're in a truck. And the truck's going, I don't know, we'll just say 40 miles an hour. 40 miles an hour this way. And then attached to this truck, in the truck of the bed, is a air cannon that shoots a soccer ball out the back at 40 miles an hour. So I got a truck going 40 miles an hour this way. Shoot a cannonball, not a cannonball, sorry, soccer ball out the back at 40 miles an hour. What do we see? Like, how fast is the cannonball going? Like, these are all I keep saying cannonball. How fast is the soccer ball going?
I have a feeling.
Oh, sorry. I don't think that was enough to flag it. But it's funny because it'll analyze my videos when I post them and it'll be like, nope. All right. All motion is relative to an observer. So truck is being, I already said this, but truck is being driven at the same speed but opposite directions. So how fast is the ball traveling depends on frame of reference. Are you in the truck or are you outside the truck? Outside the truck, which is the video they post. They actually show it from different angles. They show it from the back of the truck and they show it from if you're out of the truck. From out of the truck. So this is going to sound funny, but what is the relative speed of the ball measured outside the truck? Well, why can't we just ask how fast is the ball going? Because it depends on where you are. Are you in the truck or are you outside the truck? You're going to see different things. So what is the relative speed of the ball measured outside the truck? Well, if the truck was going 40 this way and the ball was shot 40 this way, you get 0 and the ball just drops. Um, That's relative motion. That's the vector stuff that we talked about, vector analysis, the vector addition. You got 40 one way, 40 the other way. You're going to get zero. What's the relative speed of the ball measured from someone on the truck? Well, on the truck's still moving at 40. They're going to measure that ball going 40. Uh, it's going to look like it just, but like it, from the truck's perspective, it looks, if the truck were at rest and just shot the cannonball out, it would do this. The truck sees the same thing even when it's moving. So from the truck's frame of reference, you would say it's 40 miles per hour. What if the ball was thrown in the same direction as the car? Here's what things, now you add them. You'd get 40 plus 40 and you get 80 miles per hour, which on Earth, fortunately, there is a ton of atmosphere that's going to drag that thing down. So crazy people don't throw stuff out of their car. People throw stuff out of their car. You shouldn't, but if your car's going 60 and you throw something out of it at 10, even if just a little chuck, in the same direction of the car, for a split second, that thing's going 70 miles an hour. Now, air resistance is pretty quick to affect it, and it's going to slow it down pretty quickly. But if someone's right there, like right a couple feet away from you, you just chuck this thing, you're going to hurt them. Now on the moon, no atmosphere. So if you're driving around on the moon with 40 miles an hour and you throw something to 10 miles an hour, that thing's going to go flying off at 50 miles an hour. What is the ball's real speed? It's not. It doesn't have a real speed. It has a relative speed. Who are we talking about? Is it are you on the sidewalk watching this happen, or are you on the truck watching this happen? Does it only look like it's going different speeds? No, you would, if you had a radar detector to measure these things, you would get from the truck. They'd point that radar gun at the ball. They'd measure 40. You sitting there watching this thing, you would watch it. It would fall. It would have a falling speed, but it would not have a left and right speed. You would just measure zero. The videos again, I can show. Well, here, I'll give you examples. The moving walkways or treadmills, right? The walkway's moving one way and you walk the other way. You can stay exactly where you are, right? That's the same thing as what the Mythbusters did with the truck. If the walkway's going 2 miles an hour one way and you're walking 2 miles an hour the other way, it's zero. If you walk 2 miles per hour with it and it's going 2 miles per hour with it, then 2 plus 2 is 4. You go 4 miles per hour and you get through the airport faster. This video I can show you. The other one I think is a copyright. This one I took at Busch Gardens. It's the ride, right? The Roman Rapids. The ride moves with the platform. So the ride and the platform are moving together side by side. So to you, the speed of that ride is zero, right? You're on a moving platform that's moving with the ride. So if that thing's going 2 miles an hour and you're going 2 miles per hour side by side, you get zero. And you can walk off and on that thing like it's not moving. Now, stepping onto the platform takes a second because it's like, stepping on anything that's moving. It's a little tricky. Oh, can't. Hopefully that's not enough. Hopefully that's not enough to flag it. It's a person swimming in a river, or maybe you've canoed or whatever. If you go against the stream, it's a lot harder, right? Because it's pushing against you. You go with the current, then you go a lot faster. And then that's all relative motion. I can't. Here we go. So here is, outside of my silly little examples, is relative motion ever like a problem or something you have to deal with? And the best example, this is a lame picture, but the best examples I can give you, if you are piloting a boat, you need to be concerned about depending on the boat, you definitely have to be concerned about the water current, but you could also have to be throwing the wind current. And so then that's relative motion. How fast the boat's going with the water, with the wind. Airplanes definitely have to deal with wind velocity. If you're going with the wind, against the wind, sideways to the wind, like it's going to change, it's going to push on the plane and change its motion. So it can be, it does occur in our everyday. It's not like these random little side things. And then the jets, how the jets refuel midair, right? They match speeds. Now there's still complicated. You still got air blowing it around and stuff. So it's not an easy thing to do, but you match speeds. If that thing goes 100 and you go 100, to each other, you're going 0. Drive down the road, you're going 60, the person beside you going 60. It's like they're sitting right next to you. Like you're right. You ignore the the surroundings are moving to you and the person to the car. You're not moving. Class kicks. We're gonna do some constant motion reviews. The quizzes, they are anonymous. I've turned off the leaderboard. If it's never not off, let me know and I'll see if I can go back and turn it off, but it has nothing to do with any of that. I just want to reinforce all this information in a way that you can just practice at your own pace. So it's unlimited attempts. There's no time limit except for when it's eventually due, but there's no question time limit. And then that is the end, guys. All right, let me know.